In this video, I'm going to explain three-phase power, and there's three-phase power. There's two ways that you can achieve it. You can either do a delta shape or a Y shape. And three-phase power follows the idea that if I have a current wave or a voltage wave, but it's going to be changing over time with sign. So realistically, if we're trying to power something, if we just use one wave, there'd be a dead zone here where there's not any current or voltage that we're receiving. The way that we ideally try to fix this is by adding two more waves that go in between here. I didn't draw that very well, but there's two more waves that go in between here. So then we're always positive and there's no dead zone there, okay? That's the basic idea of three-phase power. We use three specifically because that's a good balance between being efficient, because it takes power to power three lines, and having a consistent number still. So that's what three-phase power is. The two ways that we can achieve it are a delta or a Y shape. And there's four terms that I'm going to help use to help explain these. So as you guys saw from our wave here, if I draw this again, we have our curve. There's one starting right here, one starting out at 120, and this one would ideally be starting back at negative 120 if there's three of them over 360 degrees, okay? So I am going to have three, they're called power, three line sources, okay? So I have three lines that are going into this, right? If I have a generator that's making three lines of power, I'm gonna have one line, two line, three line. They're gonna be varying by 120 degrees. That's shown as easy as I could here with 120, 0, and negative 120, okay? Those are three source lines, okay? The simple idea across those is we have our line current, that's the current across the line from the source, and we have our line voltage, that's the difference in the voltage between our two source lines, okay? Then these are looking at the delta first maybe. We're gonna have all three of those are gonna come together, but the voltage from the top is gonna go this way, voltage from there is gonna go this way, voltage from there is originally gonna go this way. That's the way they're originally going to go. But then all three of them are gonna become connected, and that's where we get our three-phase power from, okay? In our Y shape, all three of them are just gonna go directly to one point, and that's what's gonna cause this shape, okay? So then once all of these are connected, we have our phase current, that's the current across my load. And then I have my phase voltage, that's the voltage difference on the two sides of the load, okay? Those ideas are a little bit different than what they're usually called or how they're explained, but I like this way because it works for both Y and delta, okay? So if we can find those three and understand those shapes, then we use these equations from it, okay? So VL equals VP in this case. In this case, the voltage is constant because notice my voltage is still going, okay? But my current is different. In this, in the Y, my current is constant because all three current sources are going to one point. It's gonna hold the same current. But my voltage is different because all three of my voltages are adding up to just 1 point now, okay? That's where those differences come from. But just use these equations. If we know VL equals VP or VL equals VP to the square root of 3, and then I'm gonna get to the plus or minus 30 in a minute, then we can just use these equations with our impedances to solve for these things. I'm not gonna go through those equations, you guys can see them. Then all VPs and IPs are the same. So when we're drawing our voltage or our current, when we have a number out here, this followed by an angle, I mean to say that this number is the same, this number is what's plus or minus 120, okay? So we get that plus or minus 120 looking at which of these we're coming from. So it's usually given in a problem like the source of BCA, okay? So if I label them here A, B, and C, it's going from B through C to A, okay? If we draw that out, because we have the angles 0, negative 120, and 120, if I drew B at 0 degrees, A at 120 degrees, and C at negative 120 degrees, in order to go from B to C to A, that means I'm starting here and I'm ending here. That would be plus 120 degrees, okay? That's a positive 120 degree change. So if I started at something like 40, then I'm gonna go up to 160, okay? So that means whatever my current is from one source, I'm gonna add that 120 to the next source, okay? In this case, if I was looking at C, B, A, this is actually going back 120 degrees to go from C to A. So that's a negative 120 degree change, okay? That's going to be consistent across the entire graph because you're gonna try to find the current here, here, and here. You're gonna find all three of the currents somewhere, and the difference between those is your 120, okay? And it's either positive or negative. The reason it's positive or negative is important. A, if you're adding 120 degrees or subtracting it, and B, that's gonna tell you if it's positive or negative as to whether you add or subtract 30 degrees, okay? If it's positive, you actually, let me write this out. If it's positive, you subtract 30 degrees. If it's negative, you add 30 degrees, okay? It's the inverse over here for voltage. That makes sense because this is the opposite, okay? So, I think that makes sense. It's kind of complicated and there's a lot going on with the 120s as far as positives or negatives, but I think you need to try to look because you're going to be solving for all three of these.